Our first lesson is on the transformations of functions. So to do that, we're going to talk about some parent functions, and one is the quadratic function, and the most basic form of that would be f of x equals x squared, or y equals x squared. So we're going to make a table of values, and the most typical numbers that we choose are -2, -1, 0, 1, and 2. So if I were to plug -2 in, -2 times -2, or -2 squared is a +4. -1 squared, -1 times -1 is 1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. So here's our points that we're going to plot. We're going to plot -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. So this is not exactly straight lines. These will look like curves. It's going to look like this. Right, we use arrows to show that it's going to keep going. We just only plotted those 5 points. So this is the graph of the parent function of a quadratic function. And here's another kind, it's absolute values. Remember, these bars mean it's the distance from 0, or it means it's always the positive value of whatever's inside. So if I were to put -2 inside, -2, the positive version of that is 2. The positive version of -1 is 1. The positive version of 0 is just 0, nothing to do there. 1 is 1, and 2 is 2. So now we're going to plot -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. So these are straight lines, and it's going to look more like a V than a U. Right? That's our absolute value function. So function families are a family of functions is made up of functions with certain characteristics. So like quadratics are a function family. Absolute value are a function family. The parent function is the simplest form of that function. And all other forms or all other equations are just transformations of their parent function. So here we have the linear family, where it's normally f of x equals x. Right, so that's a straight line. So the domain, remember, input for domain would be all real numbers. Any number can go in. And then the range would be all real numbers as well. Any number comes out, right? It goes forever down. It goes forever up. So that range is all. It goes forever right. It goes forever left. That domain is all. For absolute value, the domain is also all of our numbers, right? We're going to go everything to the left and everything to the right. But you notice here, it didn't go down at all. It only went up. So this was y is greater than or equal to 0. And our last one, the quadratic, our U shape, right? Anything goes into the left, anything goes into the right. So that's all real numbers. But again, there's nothing going down. So it's everything above the 0. We're going to be using something called interval notation this year. So all real numbers would really be written as -infinity to infinity. And we use parentheses to show that it's not actually equal to infinity because there is no real actual number of infinity. But if it's actually equal to the number, we're going to use a square bracket. So this 0 is the lowest, so it's equal to 0. But then it goes forever to the positive infinity, so that would get the parentheses. So that's kind of what that would look like, right? All real numbers again, -infinity to infinity, and y is greater than or equal to 0, so 0 is the bottom number, and it goes all the way up to positive infinity. The transformations that can occur, they can change the size, shape, position, or orientation. So if we add a number after the x, it's not added to the x, it's added after the x or after the function, that's a vertical translation, up or down. Positive is up, negative is down. If it's with the x, right, inside the parentheses with the x, happening to the x, that's a horizontal translation. And it's actually the opposite of what you would think. Plus a number inside really means going left that many units, and minus the number really means going right that many units. So up and down were the normal signs, but left and right are going to be the opposite of what you would normally think. If we're putting a negative in front of the whole thing, right, we're really doing negative to the y, that's a reflection over the x-axis. And if I put the negative in with the x inside the parentheses, that's a reflection over the y-axis. If there's a number in front of the whole thing, right, it's not just applied to the x, it's applied to the whole thing, then that's a vertical stretch or shrink. We use the word shrink or compression. So if it's bigger than 1, its absolute value, then it's going to be a stretch. It's going to make it more narrow. And if it's between 0 and 1, it's a shrink or compression. It's going to make it more wide. And then we can also have a horizontal stretch and shrink if it's to the x. But again, anything with the x lies, it's really the opposite. So if it was b, if it's greater than 1, it's really the shrink. And it's between 0 and 1, it's really the stretch. What we would really do is I would take the reciprocal of that number first and then decide if it's a stretch or shrink the way we would have for our vertical. I think it's easier that way, right? Because they're showing it as 1 over b. So I just think of it as do the reciprocal right away, and we can check if it's a stretch or a shrink. So just a reminder, anything that happens inside the function and attached to x is a horizontal something. Anything outside the function and affecting y is a vertical something. So for example 1, for each graph, we're going to describe the transformation and then write a function for the graph as a transformation of f of x. So if my f of x is the red graph here, my new graph had the same point on that line, but now it's up 3 units. So that's what happened. We went up 3. And what I can write for the new function is this was f of x, but we moved it up 3. So remember, vertical changes don't happen to the x, they happen to the whole thing. So this would be f of x plus 3. Just so you know, another way we could have written this is just like g of x equals, and if the original one was the absolute value of x, right, if that's what f of x was, then this would be the absolute value of x plus 3. But for now, we're going to focus on writing it in terms of the original function. But just know it could ask for either way. All right, so for b, here we have our quadratic function, but it's not necessary to know that. All we need to know is that from this graph to this one, if we take a look at that same kind of point, it went to the right 2. So this is happening to the x. So it's going to happen inside the parentheses with the x. And to the right 2, think of what's opposite of going to the right, right? This is normally positive, so we're going to think negative 2. All right, for one more, this did a few things, right? We went from here to here. So there's left 5 is one thing that happened. It went up to 7, and it flipped, right? It flipped over the x-axis. So we did a reflection over the x-axis. So remember, the reflection happens to the whole thing, so that's just going to go out front. What goes left and right happens to the x. So left 5, opposite of negative 5 would be plus 5. And then we went up 7, so plus 7 afterwards. So there's 2 here for you to try. You can pause, give them a try. The answers are posted on Google Classroom in the blank notes at the very end. All right, so here's some reminders. Quadratic functions can be written in what's called vertex form, which would be this form right here. F of x equals a on the outside, parentheses, x minus h squared plus k. And an absolute value function is written in this form, and it looks the same, right? It looks very similar. The only difference is we now have the bars instead of the squared. So for both of them, we can identify what's called the vertex as h comma k. And I'm just going to go back to those last 3 examples. That point that I used for all 3 of them is the vertex. It's where it changes direction, right? It's the very pointy part of the V, or it's the very turning point of the U. So h comma k will be the vertex for each of them. So the h is what shifts it left and right, right? But it's the opposite sign, so that's why it was an h, a minus inside, because then it's positive when we take it out. It's the opposite sign. K is our up and our down, right? So that's the y value of our vertex. And then A in front would be any vertical stretch or shrink. And if it was a negative, it would also include a reflection over the x-axis. So let's look at these. We're going to identify the function family. We're going to describe the transformations and say what the vertex is. So the first one, I see a squared there. So my function family is quadratic. The transformations. So I see a +4 inside. So that would be left 4. Right? Opposite of positive, left 4. And then +1 would be up 1. And then the vertex, it's an ordered pair, so we're going to write it with the parentheses, was -4, comma, +1. And that makes sense that if I shifted it to the left 4 and up 1, that would put me at -4, comma, 1 on the graph. So for my second one, this is absolute value bars. So this is an absolute value function family. We have the 2 out front, so that is a vertical, and I'm going to say it's a stretch because it's bigger than 1. So we usually put the factor by which it's the stretch or the shrink with it. So this is a vertical stretch of 2. The -3 inside with the x would tell me I'm going to the right 3. And then the -4 tells me I'm going down 4. And my vertex would be +3, -4. I'm going to change how our page looks for a second here, just so we have some room. Okay, so for our last one here, I see the square, the squaring, the parentheses with the squaring. So we're going to say this is a quadratic function family. There's a negative, so we have a reflection over the x-axis. The 1/2 is again out front. It's not inside of the x, so that's a vertical. And because it's between 0 and 1, that's going to be a shrink of 1/2. +1 means left 1, and the +3 means up 3. And then our vertex would be -1, +3. So notice for all of these, the A value did not affect my vertex at all. So when we're graphing functions using transformations, we'll create a table of values for the parent function, right? And we're usually going to use that -2, -1, 0, 1, 2. You can choose to change that if you know that you are going to be placing, if your new equation is going to have a fraction in it, right? So if you know that you had a vertical stretch, shrink, for example, and you know you want to get rid of that fraction, you can choose to put numbers that have that denominator as their factors. But we do like to keep 0 as one of them, and we pick 2 before and 2 after. We're going to change the x's and the y's based on the new function. And we'll show you what that means. And then remember, we're always doing the opposite to anything with the x's. So for example 3, we're going to go back and see the whole page again. Describe the transformation, graph, state the vertex, and domain and range. So my transformations first, I had +4 inside, so that was left 4, and -1 outside, so down 1. My parent function, I'm not going to have any fractions. I'm not going to worry about that. I'm also just going to keep it -2, -1, 0, 1, 2 for everything here, but you are free to put different numbers in if you'd like. And we know from our parent function originally that was 4, 1, 0, 1, 4. This is something you're going to want to know. You could certainly plug it in every time to an x squared, but it's easy if you just know what that parent function looks like. So what I'm going to do is I'm now going to, I'll graph my original so I see what it looked like. So I have something to compare it to. All right. So if this was x +4, what I'm going to do here is I'm going to do x -4, right? X's always get the opposite. And on the outside, I had -1, so what I'm going to do is y minus 1. I'm going to take all the numbers that were in my x column, and I'm going to take 4 away from them. So -2 minus 4 is -6. We get -5, -4, -3, -2. And I'm going to take everything in the y column, and I'm going to -1. So that's 3, 0, -1, 0, 3. It should still follow the same pattern as before, right? These were all one apart like these were. These are going one number in the middle, those two match, just like before. So I'm going to graph -6, 3, -5, 0, -4, -1, -3, 0, and -2, 3. So you notice my picture looks the same shape. It's just now moved left 4 and down 1, which is what we said the transformations were. So my vertex, it should be my middle number because originally 0, 0 was my middle number. So -4, -1. Again, if we check up here, opposite of +4, comma -1. My domain will always be that -infinity to infinity for a non-application problem. So as long as it's not a word problem that has some sort of restriction on it, our domain's always going to be -infinity to infinity. And here, my range, it's everything above this bottom number. And this bottom number was y is -1. So the bottom of my range was -1, and the arrows went up forever to infinity. So here's one for you to try. You can pause. The answers will be posted in the blank notes at the end. So for example 4, this is now an absolute value function. So we do have to keep that in mind when we make our table of values for the parent function. My transformations, there's a 2 inside with the x. So that is a horizontal, right? It's not vertical because it's not happening to the y, it's happening to the x, so it's horizontal. And the reciprocal of 2 is 1/2, so that's a shrink. Okay, so it's a horizontal shrink of 1/2, and the -2 is happening after it, so that's down 2. So my original, we said -2, -1, 0, 1, 2, and for absolute value, that's just the positive numbers. If I were to graph this, this is what it would have looked like. So now the opposite here of the 2x would be 1/2 x. So this is one of those cases where if you didn't want to have to deal with fractions, I probably would have done -4, -2, 0, 2, 4, because then when I know I'm taking half of them later on, it'll be nicer numbers for me. But if you don't have the forethought for that, or you don't care, it's fine. We're okay to have -1/2. That's going to be just fine. The y is just the -2. So half of -2 is -1, half of -1 is -0.5, half of 0 is 0, half of 1 is 0.5, and half of 2 is 1. And then 2 minus 2 is 0, 1 minus 2 is -1, 0 minus 2 is -2, -1, 0. So I'm going to graph -1, 0, -0.5, -1, 0, -2, 0.5, -1, and 1, 0. So you can see it did move down 2, and it got more narrow, which is what a horizontal shrink does. It's kind of equivalent to a vertical stretch. My vertex was 0, -2. My domain was all real numbers. And my range, the lowest I went here was -2, and I went all the way up to infinity. All right, 2 more together, and then there's one last one for you to try. So here we have another absolute value. We have the 2 in front, so that we know that that's a vertical, bigger than 1, stretch of 2. The 2 inside means left and right, and because it's positive, it's left 2, and the 3 outside is up and down, and because it's positive, it's up 3. So absolute value, when we do -2, -1, 0, 1, 2, we have 2, 1, 0, 1, 2. All right, graph that parent function. So if we're going to do only with the x is the -2. And because this was not on the x, it was on the whole thing, it was on the y, it's going to be 2y plus 3. So my x's will be -4, -3, -2, -1, and 0. And then my y's. So 2 times 2 is 4, plus 3 is 7. 2 times 1 is 2, plus 3 is 5. 2 times 0 is 0, plus 3 is 3, 5, 7. So we're going to have -4, 7, -3, 5, -2, 3, -1, 5, and 0, 7. Again, more narrow. Vertical stretch makes it more narrow. It went left 2, up 3, left 2, up 3. So my vertex was -2, 3. Domain, just like before, all real numbers. And the range, the very lowest it went was +3. So we start at +3 and go all the way up to infinity. So the last one together, we have a negative in front. So a reflection on the x-axis. We have a number in front. So that's a vertical. And because it's between 0 and 1, it's a shrink. So of 1/2. 2 inside, negative is to the right. No, I wrote that right too. And then down 4. It's a quadratic. So it's going to be +4, +1, 0, 1, 4. So the only thing happening to the x is the -2 opposite would be +2. I have a -1/2 y -4. So now adding 2, we get 0, we get 1, we get 2, we get 3, we get 4. -1/2 of 4 is -2, -4 is -6. -1/2 times 1 is -1/2, -4 is -4.5. -1/2 times 0 is 0, -4 is -4, and then these should now repeat. So my original, which I forgot to graph, had looked like this. And now my transformed function, we have 0, -6, 1, -4.5, 2, -4, 3, -4.5, and 5, -6. All right, notice this is wider than that one was because we had our vertical shrink, and it moved to the right 2 and down 4. So my vertex was 2, -4. My domain, still -infinity to infinity, all my numbers. The range this time, it has a top, which means it has a highest value. The second number in our range will be the 4, because that's the most it reaches. Everything else was below it, so everything else went down to -infinity. So this one, when it's pointing down like this, will have the -infinity first and the number second. When it points up, we have the number first and the infinity second. All right, should always be least to greatest. So there's one final one for you to try. You can go ahead and try it. Answers are posted at the end of the blank notes on Google Classroom. And that is transformations.